Hello everybody. So in this video we're going to prove the last version of Hilbert's Nullstellensatz. We're going to prove the fifth version, which says that if K is an algebraically closed field, and we assume that we have a proper ideal of the polynomial ring, then we have this equality of ideals. And so in case you're not familiar with the definitions of these V's and I's, let me just briefly recall those. Okay, so if I is an ideal, then I think we already talked about those V of I. These are the so-called algebraic sets, and these are by definition they consist of all the n tuples in the affine n space such that they kill every polynomial in I. And if X is a subset of the affine n space, then this I of X is in some sense the dual version of this guy over here. So it consists of all the polynomials in our ring such that they kill every element in X, right? So the fifth version says that we have this equality over here, and in fact I'm only going to prove the non-trivial inclusion, because the other one is pretty simple. So the easy inclusion is that the radical of I is a subset of this guy over here, and this is pretty easy to see, so I'm going to completely ignore it, and I'm going to prove the other inclusion. Okay, so let f be a polynomial living in this ideal. So yeah, I should have mentioned that. Yeah, of course, I didn't really mention it, but I'm not going to prove it. But it's easy to see that this I of X is always an ideal of the polynomial ring, right? Okay. So let f be an element in this ideal, and we want to show eventually that f lives in the radical of I, which means that we have to find the power of f that lives inside of I. Okay, so the first simple observation is we have to remind ourselves that the polynomial ring is in fact an Noetherian ring, which means that it's finitely generated, and therefore the ideal I can be generated by some polynomial. So let me just write. So let's assume that the ideal I is generated by these polynomials. Right, and of course, these are polynomials in n variables, because this is actually going to be important, because the idea, I mean, the trick is this is the so-called strong version, and I'm going to use Rabinowitz's trick. So what I'm really doing is that I'm going to define an ideal, but this is going to be an ideal of the polynomial ring in n+1 variables. Right, so it's important that these guys have n variables. Okay, so this is going to be, okay, let's call this relation 1, and now we define an ideal J. So this is by definition, this is going to be the ideal generated by these guys over here, but now I'm going to add another polynomial, and in particular I'm going to add this polynomial over here, right? So since we added this extra variable, now this becomes an ideal in the polynomial ring in n+1 variables. Okay, now the claim, I claim that in reality, V of J is an empty set. There's nothing living inside of V of J, right? So let's see why this is true. Okay, so let P be an element in V of J, right? Since now, if something lives, we have a point, and that point kills every polynomial in here, of course, in particular, it kills every fj, right? And therefore, so what I'm saying is that since V of J is a subset of V of I, we have that P lives in V of I. Okay. But we assume that F lives in here, and therefore by assumption we have that so relation 1 is equivalent to the following fact. If I take the polynomial f and I evaluate it at any element of V of I, then I'm going to get 0, right? This follows from the definitions, right? Okay. But now, since this is true for every element of V of I, then this P that we assume that lived in V of J, this P is going to kill F, right? So F of P is equal to 0, right? Right. So now let's use our assumption that P is an element of V of J, right? So P lives in V of J implies that P kills every polynomial in here, and in particular is going to kill this last polynomial. So in other words, if I take this polynomial and I evaluate it at P, I'm going to get 0, right? But as we just saw, f of P is equal to 0, right? And therefore we get that -1 is equal to 0, which is of course doesn't make any sense, and therefore V of J has to be the empty set. Okay, and now the idea is to make use of the fourth version of Nullstellensatz, right? So let me just recall that. Maybe I should write it down here. Okay, so so the fourth version said that if J was an ideal in a proper ideal in some polynomial ring, then V of J was not the empty set, right? This was the fourth version of Hilbert's Nullstellensatz. So since we proved that in our case V of J is the empty set, so in particular in our case we get that that this ideal J has to be the whole ring, right? The polynomial ring in n+1 variables, right? Hence V of J, oh, excuse me, J has to be the whole ring, right? n+1 variables. Okay, so now since so J has to be equal with the polynomial ring. So in particular, this implies that 1, the constant polynomial 1, has to live in J, right? So 1 has to be an element of J. And now, if you recall the definition of J, this clearly implies that we have some polynomials B, B1, Bm in n+1 variables, such that such that 1 is a combination of those things, right? So b times this last polynomial over here. Right, let's call this, I think I should have, yeah, let's call this relation 3, even though I should have called it relation 2, but anyway. Okay. So we have this relation, right? And now the idea is that we're going to define a ring homomorphism that's, and then we're going to apply this ring homomorphism, which I'm going to call phi, to this equation here, and somehow we're going to kill this. We're going to destroy this this guy over here, right? So let's define a ring homomorphism. I'm going to call him phi, and this is going to be a homomorphism going from from the polynomial ring in n+1 variables, and I'm going to send it to the function field of the polynomial ring in n variables, right? And this is going to be okay. So first of all, I'm sending all the constant polynomials to themselves. I'm also sending the first n variables to themselves. But now the last step is to send the last variable xn+1, to send it to 1 over f. Right? Okay. So this is easily seen to be a homomorphism of rings, and now we apply phi to relation 3. Okay, so let's for the moment forget this term over here, and let's just look what happens to this guy. So as we said, phi is a ring homomorphism, so it's going to pass through this parenthesis, and xn+1 is going to be sent to 1 over f, and therefore the f's here are going to cancel, and we're going to get 1 minus 1, which is 0, and therefore this term is going to be completely gone, right? And therefore what we get is, again, we have this sum, but now the polynomials, remember that how these bi's were actually, they actually have n+1 variables, right? And since the only thing that changes is the last variable, then these are going to be exactly the same as before. So they're going to have the first n variables, but now the last one is going to be replaced by 1 over f, right? And of course, since the fi's are polynomials in n variables, they're not going to change at all. So this is equal to 1, right? Okay. Now let's see. So we let me be something that's at least as big as the maximal of all the degrees of the bi, where I see the bi's as polynomials in the variable xn+1. Right? Okay, so now what do? We simply multiply this equation, this last equation, with f to the power of this guy over here, right? Multiply this guy with f to the power of this guy. And now what's going to happen? So, I mean, what we get is that this is going to be equal to some polynomials ai times fi, right? And these ai are going to be, by definition, right? But now, since we chose this guy to be at least as big as this maximum, then it's easy to see that every denominator of the any bi is going to be vanished, simply because I'm multiplying with f to the power of this guy, right? And therefore these are polynomials in n variables. They don't have denominators, and they definitely don't have this xn+1. So in other words, we showed that some power of f is an element in I, because I was by definition the ideal generated by these fi, right? And this of course implies that f has to be an element of the radical, and this finishes the proof of the fifth and last version of Hilbert's Nullstellensatz. And yeah, that was it. Thank you for watching.